Thank you, and welcome back. Okay, so since almost everybody here is, well, 60% of the audience is a member of VALIS, I'm going to dispense with a lot of introductions, and I'm not going to really much speak about the detector, but I'll talk about a lot of results that we have. Building up the notion that we have essentially thermalized systems, and then what we can do and understand about these systems. Just a very quick introduction. What is this about? Well, this is about understanding what matter is made of, and you can, if you look around you, you see all kinds of manifestation of what matter is. You see it in solid forms, liquid form, gas, and we know about the sun being a plasma, and now we know about the coagulant plasma. So what is this about? Well, this, as you know, we've been on this quest now since these guys started a long time ago, more than 2,000 years ago, and they're trying to understand what stuff is made of, and they had a very nice answer, easy to memorize. But of course, we know it's a little simplistic. Note that there were two guys, these two gentlemen, who had realized that there must be atoms. They reasoned their way into thinking there must be atoms. They were right. So I'm going to cut to, through 2,000 years of history of science. So the view that we have today of matter is that, of course, it's made of atoms, and within the atoms, thanks to Mr. Rutherford, we know there's a nucleus, and thanks to Mr. Chadwick, we know there's a neutron, and I forget who discovered the electron, and so on. And so now we have this view of matter, that nuclei are made of protons and neutrons, made of quarks, bound together by the strong nuclear force, and in the form of gluons. And so we also know that these quarks and leptons form all these types of objects, nuclei, composite particles in categories of baryons and mesons, and we also have leptons and so on. And most recently we discovered the Higgs baryon. So I'm going to go very quickly through this. Now so we have a theory for the strong interaction. It's called quantum chromodynamics. There's a Lagrangian, and this Lagrangian has several terms, and these terms involve a coupling, and this coupling now is known to vary. The strength of the coupling is known to vary with the momentum transfer, and so at very low momentum transfer, or for systems that are fairly large, you have very strong coupling. This coupling binds the proton together and many other elementary particles. But as you increase the momentum transfer, the coupling becomes vanishingly small, and so that means that at high momentum transfer, then the system, the interactions become almost perturbative in their nature. You can actually calculate them with perturbative theory, and you can then study the matter more easily. And so this, one thing leading to another, this led to the notion that maybe if we had a system before I say this leads to the notion of confinement. So at low momentum transfer, you have very strong interaction. You have confinement of the quarks. And at very high momentum transfer, the coupling becoming very small, you have what's known as asymptotic freedom, which means that you have weakish interaction. And so in principle, you can break down the protons and neutrons into forming some large objects. So that's been the name of the game now for more than 30 years. The idea is that can we form a system, a very large system that would be made of quarks, but not protons and neutrons. In other words, can we reach a temperature and some energy density such that we would have a system that is composed of asymptotically, quote unquote, free quarks. And so it's been a quest to try to reach the amount of, or reach the temperature that such that we can achieve this transition. So the idea is that you have, at low temperature, you have a system, a nucleus composed of neutrons and protons, each of them with 3 quarks. As you raise the temperature, these quarks then, these protons and neutrons collide. As they collide, the quarks for the duration of the collision can become, can roam about and become essentially free. So you have the notion of the coagulant plasma. So this leads to the notion of having phases. I don't have to dwell on the fact that with water, for instance, we have 3 phases, solid, liquid, and gas, with transition between these different phases, and a critical point, a critical point. And so these phases are first order phases. They have a latent heat, and so which means that when you reach the temperature of fusion or temperature of vaporization, you have to supply heat to transform the system and transform the system into from one phase to the other. By analogy, then one can look at a phase diagram of QCD matter / nuclear matter. Here I have the temperature as a function of the baryon chemical potential, but you can think of this for the purpose of this discussion as the density of matter. And so the idea is that the temperature scale here is in MeV. Consequently, it's a very large temperature scale. And we find ourselves, the matter in this room finds itself here. And through various consideration, people came to the understanding that there should be somewhere in this phase diagram, there should be somewhere a phase transition from what we would call a hadron gas, that is matter made of hadrons, protons, neutrons, mesons, and so on. And at very high temperature and density, you would have another type of matter that we would call a coagulant plasma, consisting of basically free, quote unquote, free quarks and gluon. Further consideration led to the notion that some at very low density or chemical potential, this would be a crossover type transition because the strange quarks are massive. And then at higher chemical potential, one might have a first order phase transition. That is, when going from one phase to the other, you would have a discontinuity, you would have a latent heat. And so if you have a first order here and a crossover here, there must be some endpoint, and that endpoint is known as critical point of QCD. And in it, of course, many efforts have been spent both on the theory side and on the experimental side to identify the position of this critical point. If you look at this in detail, you'll find maps of people have mapped theory calculation, and you'll find that the points are all over the place. So it's very difficult from a theoretical standpoint to pin down the position of the critical point. And so what we want to do essentially is to find it experimentally. And that's really a business for the lower energy machines, such as RHIC or FAIR, where you are dealing with chemical potentials that are fairly large. And so in principle, with the beam energy scan at RHIC, beam energy scan number 1 and number 2, you can in principle map this. With FAIR, you can possibly, NICA, you can probably go a little further down. So in principle, there's a possibility of identifying the existence of a first order transition and perhaps a critical point. So far, there were claims of the existence or perhaps tantalizing evidence for the existence of the critical point, but it's it's not been fully vetted. So, what I'm going to be focusing on in this presentation is not so much this part, but this part of the diagram, where at the Large Hadron Collider with the ALICE experiment, we are forming with TeV energy scale, we are forming the system at a very high temperature, and the first thing we want to establish is that yes, there is a quark gluon plasma formed, and so we'll talk about that. And then obviously this system is not bound, there's no vessel containing the system, so the system expands. As it expands, it's cooled down. As it cools down, it crosses this transition region, and it produces hadron, and we observe those hadrons in our detector. And it is on the basis of the observation of those hadrons that we try to infer the property, well, first the existence of this quark gluon plasma, and then what are the properties of this quark gluon plasma. So the big picture of what the field, well, that's my own view, of course. The big picture of what the field is trying to achieve was first to demonstrate the existence of the phase transition into a quark gluon plasma, demonstrate the existence of the confinement, understand perhaps the nature of the phase transition, and then understand whether or not there's a critical point and where it might be. I think we have achieved proof of the existence of deconfinement, but I think we're not yet at the point where we can say that we have understood the nature of the phase transition. There was also the notion of chiral symmetry restoration, the notion that, well, every elementary particle carries a spin in the momentum, and whether the interactions they undergo are susceptible to the relative orientation. And so we know that this symmetry is broken at low temperature. It might be restored at high temperature. Is it restored at the LHC? I don't think there's any specific evidence that this is realized. Now, having established that we produce something like a quark gluon plasma, then we want to understand its properties. It turns out, as I will argue in a moment, and as I'm sure you know, that the quark gluon plasma at RHIC and at LHC doesn't behave like a quasi-free system of quarks. We're not really in the regime of asymptotic freedom. It turns out that we are still in a very strongly interacting regime, and this regime produces something that really looks like a fluid, in nearly a perfect fluid, as I will argue in a moment. So the name of the game at this point is to figure out what is the equation of state of this system, determine some of its properties, such as the heat capacity, perhaps the conductivity. Not a whole lot of work has been done in that direction, so there's a lot of opportunities there. And then a lot of work has been done in measuring the shear and bulk viscosity, and of course that's the reason we're here. And then there's much interest in determining the compressibility based on multiplicity fluctuation, but I think that's a very tough one. And then finally, people who study jets have an interest in trying to understand how very high, very energetic partons, quarks and gluon, interact with this medium, and they want to understand the energy loss or momentum loss properties of this quark gluon plasma. So I don't have to articulate the notion that one of the reasons we want to do this is we want to understand where we come from. So this is a view of the story of the universe, and within the first microseconds or few microseconds, we understand there was a quark gluon plasma, and so we would like to understand the properties of the matter at that time. It's one of my personal interests to eventually be able to understand something about the coagulant plasma that would teach us why the universe is the way it is. Could we change the properties of the coagulant plasma and end up with a different universe? That's an open question, and I've found nobody so far who can actually tell me one way or the other. So obviously the temperature that we need to achieve to study the coagulant plasma are enormously high, 100,000 times the temperature of the sun in its core. And so you can't achieve this by the usual, put something on the stove, boil it, and put your thermometer and your barometer in there. And so the only way we can achieve this kind of density and temperature is by means of nuclear collision, and the field started already more than 30 years ago at the Bevelak in Berkeley. People were already then trying to make such a coagulant plasma and find evidence for making this plasma. And then it went to the alternating radiant synchrotron at Brookhaven, and then it came to the SPS at CERN, and then it went back to RHIC at Brookhaven, and then now it's both at RHIC and at the Large Hadron Collider. And now I think we have established that perhaps at the SPS there was some evidence that some bubbles of plasma were made. The point of this slide is to emphasize that it's a tricky business, because the system that we study have to be produced at very high energy. So the first challenge is to produce these very high beam energies, which then lead to Lorentz contraction, very, very tight contraction. And of course, now we are dealing with a nuclear size system, and the crossing time of these two contracted systems will be below 1 Fermi over C, 1 femtometer per C. And so then the two nuclei cross one another. We hope and envision that they make some kind of a fireball, some kind of a plasma. And the lifetime of this plasma is of the order of 10 to the minus 22 seconds, or 20 Fermi over C. So it's a very short amount of time. And as the system expands, it produces hadron. And so the hope is that we can use those hadrons to infer something about the properties of the system before it actually fell apart. And so obviously and not only do we have to do this, we have to do this at these very high energy, and we've learned progressively, going from the Bevelak to the AGS to RHIC, to the SPS to RHIC, and then to LHC, that we've learned that the number of particles produced in these collisions is exceedingly large, and so we need detector devices that are able to handle these large multiplicities. And so that's where Alice came in with this enormous TPC, time projection chamber, and the success story of the discovery of the coagulant plasma actually started at RHIC, Brookhaven National Lab, with the STAR and Phoenix experiment. Phobos and Brahms played some role as well, but the bulk of the discoveries came from these two experiments.
Well, do you say this often at CERN?
Huh?
Do you make this statement often at CERN?
Let me put it this way. I think it's fair to argue that the evidence became extremely clear at RHIC, and it wasn't so clear at the SPS. But now when you look back at the SPS results, you can say, yeah, this feature, that look as if there was a coagulant plasma. I'm on the other side of the Atlantic, so I can. They can't reach me. Yeah. Well, the JSA suppression, it's not an easy story to tell, because there is co-mover, suppression, and so on. So it's not clear. Even today, it's not completely clear. And then, of course, I'm going to be talking about results obtained by Alice. This is a schematic of the detector, very large magnet, time projection chamber, it's really an omnipurpose device capable of a very large array of measurement types. And I'm not going to describe each of these detectors, just to tell you that we can measure momenta of charged particle from essentially from 0.2, 0.15 MeV all the way up to hundreds of GeV. We can measure thousands of particle per collisions. We can measure we can identify the particles and so on and so forth. So it's a very well designed, very well built and operated machine. It's fantastic. I will say this, much better than STAR. But I don't say that at Brookhaven. Okay, so we've been taking data for quite a while now, and we have data in lead lead, xenon, p-lead, pp, and we've been very successful in analyzing the data and producing papers. I didn't update this slide. This is an old slide, but we're already at 100. And well, actually, I did update. As of last Quark Matter, we were at 186 publications. For 10 years, it's not bad. Obviously, if you divide by 1,000, it's not great, but I think it's good. So, so again, the name of the game and what I'm going to focus on here is proof of existence. Not so much the nature of the phase transition, but trying to understand some of the properties and the heterochemistry of this. There's still a lot of technical questions. There are also searches for new phenomena, such as the chiral magnetic effect. I'm not covering that at all. There's some work being done to look at disoriented chiral condensate, believe it or not. And there are some interesting results coming out. And I'm not going to talk about that either. So since not everybody here is in the collaboration or an experimental Hevelian physicist, I will spend a few minutes discussing how we characterize the violence of the collisions or the centrality of the collision. I mean, the point of going to heavy ion collisions is that we can form a system that is enormous, that is very, very large, but it also gives us the opportunity to look at how the physics that we're studying changes when we vary the impact parameter of the collision. So if you have one nucleus coming out, one nucleus going into the page, the impact parameter here can be, we don't control it, the beam happen to hit one another. So randomly, this impact parameter can be 0 or twice the radius of the nuclei. And now we have essentially two regions. We have a region where the two nuclei will overlap. We call that the participant region. And we have two regions where they don't overlap. We call that the spectator. Why do we say spectator? The wavelength associated with these TeV energy particle is extremely short. The time of collision is extremely short. And so at the speed of light, it would take many Fermi over C to communicate the information that something has been colliding. And so the collision will take place, and the information that the collision has taken place will take time to propagate to the other side of the nucleus, but by the time it has propagated there, the nucleus is gone. And so these nucleons are not really involved in the collision, neither are these here. Only these nucleons are involved in the collisions. So we can characterize then the collisions based on this impact parameter, which we don't control, but we can measure by looking at the number of particles that this region of participants will, the number of particles it produces. The number of particles that it produces will be proportional to the number of neutrons or protons that are interacting with one another. And so the more of these neutrons and protons interact, the larger the multiplicity will be, and consequently we can estimate at the very least the impact parameter of the collision. And we have various ways of doing this. One is by measuring the number of particles that are produced in the central region of the apparatus, and the other is by looking at the number of such spectators that are moving down, essentially down the beam direction, either in the form of neutrons or in the form of protons. So we have so-called 0-degree calorimeter to measure these particles. And so then one expects that there is a very good correlation between the energy forward and the number of particles that is measured in these, in the central region. And so this illustrates here that for different, different impact parameter, one finds different multiplicity, number of particles or multiplicity in the central region of the detector, in the TPC. And so this region here corresponds to low multiplicity. That corresponds to so-called peripheral collision or grazing collision. Here we have mid-central, and then we have here central collisions that will give us the largest multiplicities. Since it's difficult to map a number of particles onto a physical impact parameter, what we do is that we think in terms of cross-section, and so this here has a total cross-section, and then we partition this cross-section in slices as shown here, and then we can study everything else about these collisions in terms of these partitions. One more point I want to emphasize about the detector is that it has tremendous, amazingly beautiful particle identification capabilities thanks to energy loss in the TPC. So here is typical signal of energy loss as a function of momentum, and you can see very clearly bands corresponding to pions, kaons, protons, deuterons, tritons. And so you see very, very good separation between these bands all the way, not quite to 1 GeV, but certainly between pions and kaons all the way up to 700 MeV. And then on top of that, we have the time of flight detector located around the TPC. And again, here we can plot the time of flight for a particle going from the interaction vertex to the time of flight as a function of the momentum. And again, here you see very clear bands corresponding to electrons, pions, kaons, and protons. And we can also do other types of measurement where we detect particles in pairs or even in triplets, and we calculate the mass, the so-called invariant mass of these particles, and this gives us the capacity to do such spectrum here. So this is the number of counts as a function of the mass of a pair, and you see a beautiful peak here corresponding to an object that decays into two particles. Okay, so first let's start with some results from RHIC, since I said that the QGP was discovered there. It really started with very basic measurements. This measurement here shows a unidentified hadron spectrum. So H plus and H minus stands for unidentified hadron. So the cross section is plotted as a function of the transverse momentum, and it is plotted for several classes of collision centrality, as I've articulated a moment ago. And it's compared to the cross section in proton-proton collisions. Okay. Already there are very successful, beautiful results. What do you do with this? Then you ask yourself, what is the difference between the spectrum that you see in proton-proton and that you see in goal-goal collisions at RHIC? And so the way this is done is to calculate what's known as a nuclear modification factor, RAA, which is defined as the cross-section measured in AA divided by the cross-section in proton-proton collision, adjusted or scaled by the number of interaction that you expect at the given impact parameter corresponding to the collision centrality class that you're looking at. And so there was some work involved in learning how to do this properly, but this work was successful, and I will articulate why in a moment. And so this here illustrates a sample of results that was obtained and published in 2003 by the STAR collaboration, where we now have this RAA, nuclear modification factor, plotted as a function of the momentum of the particles. And it is shown in different centrality class. So 60, 80 corresponds to peripheral, 0 to 5 corresponds to most central. And what you will find, let's start with the peripheral, is that this ratio is of order 1 in the most peripheral collision. So in most peripheral collision, the overlap between the two nuclei is small, and so basically what you see is that in this case, gold-gold behaves pretty much like proton-proton. On the other hand, as you progressively increase the collision centrality or the overlap between the two nuclei, you see that this ratio is progressively changing, and so it goes a little below 1, progressively more and more below 1, and as you reach the most central collision, it's very small, much smaller than 1 of order 0.4 or 0.5. And so this suggests that something in the medium that we form has a large opacity. That is, it's blocking the particles that would normally have a high energy are interacting, losing energy, and are pushed towards lower momenta. Now, of course, one big issue that we had at the time was to make sure that we really understood this scaling factor, this TAA. And so one way that we were able to verify this is was achieved by Phoenix, actually. And so there's a ton of results. I just want to focus on one set of results, those of gammas, direct gammas. So the idea here is you measure gammas that are produced by the interaction, not gammas that are produced by decays of other particles. So it's a very challenging result. So it took quite a bit of time to obtain it, but the end result is fantastic because these are the points for photons. And so these points tell us that photons in gold-gold collisions are not attenuated, and that is exactly what you expect, because photons do not interact strongly. They interact by electromagnetic interaction. They don't have enough time, they don't have enough thickness to be attenuated by the system, so you expect indeed a RAA to be 1. And so this tells us that the calibration of TAA was correct. It also tells us that indeed the system produced in central collision is very opaque. There's something very big and opaque that is formed, and it's shifting all the momenta of the particle to a very low momentum region. This was further articulated and confirmed through this plot that I've already showed yesterday. Again, this is a correlation function as a function of the opening angle between the two particles, and as I've argued yesterday, you have the protons in black and the gold-gold results in blue. And so on the near side, the delta phi of 0, near 0, you see a peak in both PP and gold-gold, whereas on the away side, you see a nice peak in PP corresponding to back-to-back particle emission, but in gold-gold you don't see that peak. And so there is evidence that particles that were going in on the away side were absorbed by the opaque system. And this illustrates here the geometry of this. In proton-proton, you produce 2 jets, and so that's all there is, more or less. And so you can see this away side correlation, whereas in gold-gold or lead-lead, now you have formed a system illustrated by this blob. And so if you have a jet escaping on one side, the jet going on the other side now has to traverse the medium. It has to go through a lot of interactions. So that tends, if the system is opaque, it tends to quench the away side jet or suppress the away side jet. And that's exactly what we see here. Now, this was done for a relatively low range of particle momentum. If now you say, okay, let me look at very high momentum particles that I'm sure are coming from jet, but very hard particle. If particles lose energy, I still stand a chance to be able to see something on the away side, and sure enough, we do. So this was also confirmation that we knew what we were doing collectively. And so here you have the same type of correlation function where now you have the so-called trigger. So you have one particle that is very high momentum, 4 to 6, 6 to 8 GeV, 8 to 15. And you look at the associate particle, the other 3 to 4, 4 to 6. And what you find indeed is when you look at 4 to 6 here, you see not only the near side peak, but an away side peak, which tells you that somehow the jet that is going on the other side had enough energy or enough momentum to actually punch through.
I had a question left from yesterday, if you don't mind answering it at this point.
Yeah.
Which is whether you can distinguish a quark-initiated jet from a gluon-initiated jet at least.
I don't think we can do this with inclusive measurements. People have tried with doing this with identified particles, but I don't think that's very successful. So this was, in a nutshell, what Rick achieved. And then 2010, Alice came on. And so it came on, and within just a few months, we had beautiful results. I'm not going to show all of this. There's so much. It's incredible. But this shows a pion, charged pion spectrum as a function of momentum. Cross-section is a function of momentum. Again, here in different multiplicity classes. And that is to be compared to what we got in proton-proton collision at a slightly different energy. And so immediately we saw a very large array of results, not only for pions or unidentified hadrons, but also for all kinds of identified particles, pions, kaons, K-short, lambdas, K-star, phi, cascade, and omegas. And so this is a very powerful device that enables us to look at a plethora of types of particles and different aspects of what's happening in these collisions. And so the first thing that was of interest, of course, is to calculate this RAA. So this is, this is not RAA. On the left is just a spectrum comparing 70-80% centrality class, so that's peripheral. And then 0 to 5 in solid red is central. And so you can see that there's a difference. Now you correct for the number of expected collisions in central collision, and you calculate RAA, as I've already explained. And so this is RAA as a function of PT. And you can see that it has this structure here. So this is complicated region. But the punchline is that there's a lot of attenuation in this region from 5 to 20. There's lots of attenuation. And in fact, this is compared, so the red points are Alice results, the blue points and black points are Phoenix and star results. So you can see that at the system that is produced at the Large Hadron Collider energy, 2.76 TeV, there's even more suppression at the Large Hadron Collider than there was at RHIC. It was also interesting to see a linear, somewhat, well, actually it's a log scale, so a power law scale here. And people then who are in the business of trying to understand the energy loss property of the plasma spent quite a bit of time trying to understand the values of RAA and how it changes with momentum. That's a story I'm not going to tell. That's for a different talk. Like I said, we were able to study a lot of very, very many different systems, and with the power of the detector, We were able to measure a lot of different things, and we're just going to splash a few things. And so we measured proton-proton collisions, proton-lead, lead-lead collisions, and what is shown here are proton spectra. And so we can identify how protons are emitted by these three systems. We can compare them, and we can try to understand what's going on. You will note that the shape of the spectra are very different in PP than they are in lead-lead collisions. Obviously here you have to note that there's a change in the range of the scale. So this goes from 0 to 4.5, so that's this region here. So those spectra are actually different in shape, although it's not obvious from this slide. One of the interesting facet of making a coagulant plasma is that if you do make a coagulant plasma, and in principle you should be able to produce a lot of strangeness in this coagulant plasma, particularly if there was chiral symmetry restoration, if the quark masses were dropping. And so there was a lot of interest in trying to measure strange particles, and so lots of effort were put there. So this shows here the ratio of the yield of strange particles, except for this one here, which is proton and antiproton. But you have a ratio of the yield of strange particle to the yield of charged pions, and so you have kaons, lambdas, phi, cascade omegas. And so first of all, it was already an achievement to be able to see this with such a precision.
What is the point of measuring 2.5? There is lambda.
I think the point of plotting 2.5 was to enable a one-to-one comparison or apple-to-apple comparison of lambda, lambda bar, and pp bar. That's all there is. But the point of interest here is that, well, there are two points of interest. One is you start from peripheral collision to central collision on the right. In peripheral collision, the ratio, all these ratios are fairly small. And that's because making strangeness is not easy. And once you made it, binding it into these double strange and triply strange particle is actually not easy. You have to make a lot of strangeness to make an omega or an omega minus. What's spectacular is that when you go into the most central lead-lead collisions, now you have a very large abundance of these multi-strange strange particles, and so that's evidence that somehow making these objects in central collisions becomes more difficult, more simpler, so to speak. You're producing strange quarks, and you're basically filling the phase space of these quarks, these strange quarks, and so you essentially saturate the amount of strangeness that you can produce. And I will argue this more quantitatively in a moment. Like I said, there's so many results. It's hard to pick what to show. Interestingly, we can see not only elementary particles, but we also can see nuclei being produced, or not just nuclei, but also anti-nuclei being produced by lead-lead collisions. This here shows, on the left, it shows deuterons, the cross-section for deuterons as a function of PT, again in multiple centrality classes. And on the right, it shows the production of helium, again, well, in fewer centrality classes here, because producing helium is more rare, but we can actually measure it, and you can see that it's actually produced. Now, so there are multiple things to try to understand here, and I'm not going to be able to discuss everything, but one aspect is what is driving the shape of these spectra. And so to understand what's driving the shape of the spectra, one is interested in understanding how the average momentum of these particles is changing when you look at different collision classes or collision centrality classes. And so here again I have proton, 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 lead, 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 well, not just lead, lead, but I also have xenon, xenon, lead, lead, and 2.76 and 502. And I have results for pion, kaon, proton, phi, cascade, and omega. And so what is being plotted here is the average momentum of these particles. And you can see that there's a roughly linear relation between the average momentum of these particles and the multiplicity of particles produced. So in other words, the more violent the collisions are, the more particles they produce, the higher the momentum of these, the average momentum of the particles are produced. Now, in the context of a proton-proton collision, you could argue, well, we know that jets exist, specifically at these collisions. We know for a long time now that very high momentum jets are produced, and high momentum jets have large multiplicity.